Wenn man sich heute ein Mobiltelefon kauft, dann
When you buy a cell phone these days, these phones usually have an OLED display. And this is where you can see the big advantages offered by OLEDs. They provide very high contrast. In future, OLEDs are also intended to be used for general lighting purposes. OLEDs are among the extremely few light sources that we know that are truly wide area light sources.
die wirklich flächige Lichtquellen sind. Ansonsten gilt für die OLEDs,
OLEDs offer the whole range of advantages that also apply to organic solar cells. This means they provide mechanical flexibility. They allow us free choice of color. We can engineer them to be transparent, and I hope that ultimately we will even be able to print them.
The engineering office Light and Planning in the center of Karlsruhe develops lighting solutions for architects and builders. Managing Director Fatih Yetkin has a degree in architecture with a specialization in lighting design and advises his clients also with regard to organic light-emitting diodes, briefly called OLEDs. He can demonstrate the advantages of this technology by using a 10 cm by 10 cm module.
You have to imagine that an OLED is just a few millimeters thick, so that when you put it underneath a store shelf, you will achieve a perfect product presentation, because it produces essentially shadow-free lighting. You get an even, large space illumination that is very smoothly distributed over a wide area. And this is actually the big advantage of OLEDs. We haven't actually had the opportunity yet to use OLEDs, due to the price-performance ratio. Indeed, they are still very expensive.
Scientists from the Light Technology Institute at the Karlsruhe Institute of Technology are currently conducting research with the aim of making OLEDs more cost-effective and thus suitable for future large-scale production. They focus their efforts on improving the efficiency of both organic light-emitting diodes and of organic solar cells.
hier bei uns im Institut,
At our institute, a lot of work is being done in the field of lighting technology, starting from lighting technology in vehicles up to optoelectronics, which is actually at the core of our work.
organische Photovoltaik bedeutet im Prinzip,
Organic photovoltaics basically means that we use synthetic materials, plastic, such as plastic bags if you will.
organisch heißt in dem Fall,
Organic in this case means that we use compounds that are based on carbon molecules.
In an OLED, the carbon compounds form the light-emitting layer, whereas in an organic solar cell they form the light-absorbing layer. This active layer is situated between two electrodes, a cathode and an anode, which will later on collect the current. The active layer consists of a semiconductor, which, in the case of an OLED, conducts electricity only when a voltage is applied to the electrodes, and, in the case of an organic solar cell, when light is absorbed by the cell. For research purposes at the Light Technology Institute, organic light-emitting diodes and solar cells are manufactured from different components. Because the layers that are used are very thin, they are sensitive to contamination. Therefore, production takes place in a clean room, which is sealed off from the outside world and may only be entered through an airlock and with protective clothing. Scientist Daniel Baru demonstrates the manufacturing process of an organic solar cell. OLEDs can be manufactured in an analogous manner. The starting point is the anode, a coating consisting of indium tin oxide, abbreviated as ITO, deposited on a glass plate. The ITO is coated with a light-sensitive photoresist, which is developed only at the locations that are to be etched. The remaining parts will conduct the electricity later on, so the whole thing is similar to manufacturing a printed circuit board. In the first stage of the production process, Daniel Baru puts the exposed ITO layer into a container filled with half-concentrated hydrochloric acid. The acid etches away the exposed areas. Subsequently, the ITO layer is washed with distilled water. Since indium is a rare element, its use is one of the reasons for the currently high costs of organic electronics, though not the only one. Another reason is related to the size of the cells. For on the laboratory level, small cells are used that are cut to size.
ich würde sagen, die größte Herausforderung
I would say the biggest challenge in the field of organic photovoltaics is actually scaling up. That is to say, to manufacture the solar cells that we are currently able to produce on a small area in the lab with large printing machines at some point in the future.
Das heißt, wir skalieren unsere Solarzellen auf 10
This means that we're scaling up our solar cells to a 10 by 10 centimeters area, and by doing so we can show that the processes are scalable and transferable to industrial plants or industrial processes. The actual upscaling process to square meters for photovoltaic production, this will be a task for industry.
In the laboratory, scientists work with glass plates because they are more stable. Ultimately, however, the goal is to print organic electronics on flexible plastic foils. When the glass plates have been cut to size, they need to be thoroughly cleaned. For this purpose, they are immersed in acetone and isopropanol and then placed into an ultrasonic bath where they are cleaned by means of sound waves. In the next step, the glass plates are blow-dried. Before the active layer of the solar cell can be applied to the glass plate, different components have to be mixed together. For this purpose, Daniel Baro inserts an empty vial into the glove box. A vacuum is created to ensure that the box is devoid of oxygen. Scientists at the Light Technology Institute are currently conducting a large-scale project on the sustainable production of organic electronics involving the use of non-hazardous solvents.
Wenn ich in die Industrie gehe und
When I go into industry and I want to produce something on a real large scale, then I have to take care that my employees aren't poisoned by the solvents that I use. Accordingly, we have to make sure that all the work we're doing with solvents in the lab, where we don't have to worry about security, can later on also be implemented on the industrial scale.
Auf industrieller Skala umsetzen können.
Before adding the solvent, an absorbent polymer is placed into the vial. The polymer is an organic semiconductor made of carbon compounds. It is because of these carbon compounds that we speak of organic electronics. Then a solvent, such as dichlorobenzene, is added using a pipette, and the entire contents are mixed by using a shaker. In the next step, the solvent will cause the deposition of the light-emitting layer of the OLED or of the light-absorbing layer of an organic solar cell.
Da unsere organischen Halbleiter, die wir benutzen,
Since, according to ordinary standards, the organic semiconductors that we use to absorb light are actually very good insulators. These layers are very thin. We've got layers with a thickness of about 100 nanometers here.
100 Nanometern. Wenn ich mir vorstelle,
When I imagine scaling up such a typical solar cell to the size of Lake Constance, our light-absorbing layer would be just about 10 centimeters thick. That means that we need to deposit these layers, which are extremely thin, square meter by square meter in a homogeneous manner. And to achieve this homogeneous deposition over large areas, to actually produce nanotechnology square meter by square meter, that is indeed a very, very big challenge.
das ist eine sehr, sehr große Herausforderung.
The next step is the coating process, which is performed in another glove box. Once again, the vial and the glass plates must pass through an airlock and are then processed further in the nitrogen atmosphere. Daniel Baro dispenses the organic semiconductor onto the glass plate by means of spin coating. By rotating the plate at high speed, excess fluid is flung off the substrate. What remains is a thin plastic film. Spin coating is a procedure mainly used in research laboratories where work is performed on small-size substrates.
Auf der anderen Seite, wenn man in die industrielle Fertigung geht,
In industrial production, on the other hand, methods are used which are similar to plate coating. The plate coating method can be reproduced in the lab too as an intermediate step on the way to industrial production. Plate coating can be compared quite well to spreading butter on a slice of bread. I take a knife and I take some butter. I move the knife over the surface of the bread, and in this way I will create a film of butter. If I want to scale up this process, however, that is to say if I want to manufacture large solar cells, this won't work anymore, because at some point the butter on my knife will have been used up, and then you will have to proceed to the slot die coating technique, where you've got a slot in your knife which allows you to refill the butter, so that you can spread the butter continuously over very long distances. Now let's not speak of butter, but of organic semiconductors.
Now that the anode and the active layer have been applied to the glass plate, what's still lacking is the second electrode, the cathode. The cathode consists of a metal. For this purpose, the researcher applies a stripe mask to the substrate. He removes the mask again after the cathode has been thermally evaporated onto the substrate in a high vacuum chamber. In a current research project with industry, scientists want to make sure that in future the components of organic electronics will no longer need to be vacuum evaporated in a laborious process in order to make production faster and thus more cost efficient.
da geht es die Druckbarkeit der Solarzellen.
The project is about the printability of solar cells, which is actually the last ultimate step that we want to take. The aim is to print not only the active layers, that is to say the light-absorbing layers, but also the electrodes. And as a matter of fact, we also want to try to engineer the organic solar cells to be semi-transparent, so that they can be integrated into windows.
Until we get this far, however, there are some more challenges to overcome. Because the larger the modules, the bigger are the energy losses caused in the electrodes. One solution to this problem is provided by laser structuring. With this method, each individual layer of the solar cell or the light-emitting diode is cut by a laser before the next layer is applied. In this way, a large number of small cells are produced. In the cutting area, the individual cells are connected to each other by the electrodes and switched in series. By switching them in series, subsequent energy losses will be minimized, because the current will decrease while the power remains consistently high. The laser is computer-controlled and the laser beam is directed via mirrors towards the experimental setup. At the cutting point, the substrate is placed under a lens which focuses the laser beam. To verify the efficiency of an organic solar cell, it can be checked by using a solar simulator and by means of quantum efficiency measurements. The quantum efficiency is the ratio between the absorbed photons and the electrons that provide the electricity yield, depending on different wavelengths of light. The measurement begins with the short wavelengths of ultraviolet light, continues with a spectrum of visible light, ranging from purple to blue, green and yellow to red, and ends with long wavelength infrared region. Another possibility of locating defects in both solar cells and light-emitting diodes is to examine it under an atomic force microscope in the characterization lab. Here, the organic semiconductor is again inserted through an airlock into a glove box. After it has been put under a laser, scientist Stefan Reich first has to install the probe tip into a holder and to align the laser. When using an atomic force microscope, the measurement needle of the microscope is passed over the surface by the substrate. From the electrostatic interaction between the measuring needle and the surface, the computer calculates the height of the layers. On the computer, the result is displayed as a layer height profile. The atomic force microscope measures surface currents and other material properties with very high resolution. If, for example, an organic solar cell is to be tested, the scientist can measure spatially resolved photocurrents within the solar cell in order to determine which areas supply more or less power. Currently, laboratory-made organic solar cells provide an efficiency of 11.1% based on an area of 1 square centimeter. The Karlsruhe scientists are investigating a new technology aimed at enhancing the efficiency of the cells.
Ja, unser Flaggschiff momentan bei der
Well, our current flagship project is the research we are doing on organic tandem solar cells. Here we stack 2 solar cells on top of each other to further improve the absorption of light. That is to say, the light that hasn't been absorbed by the first solar cell is then absorbed by the second one.
In contrast to organic solar cells, an OLED emits light. However, since there are more similarities than differences in the production of the 2 cell types, research results can be applied to both areas. Daniel Barrow puts his laboratory result to the test by applying a voltage to the 2 terminals. The light effects show that the OLED works.
Die organische Photovoltaik ist heute nach wie vor ein Forschungsgebiet.
Today, organic photovoltaics is still an area of active research. Of course, there's a number of working groups doing research on organic photovoltaics, not only in Germany, but this is happening worldwide. Especially Europe has a leading role with regard to the research on organic solar cells. These activities are supported by the European Union, and of course, this applies to us too. Nevertheless, there are also some companies that are already active in this field, and a number of these companies, among them also German ones, say that their first pilot project for organic photovoltaics are almost ready for market entry. Of course, we're not speaking of applications such as solar cells for rooftops here. We haven't got that far yet, but of mobile applications, integration into bags or similar applications.
Oder ähnliche Anwendungen.
Other than organic solar cells, OLEDs are indeed already available on the market, but they are being used above all in display technology. With the development of cost-efficient organic electronics, OLEDs will in future also conquer the general lighting market.
Dadurch, dass die OLED nur wenige Millimeter dick ist.
Due to the fact that OLEDs are just a few millimeters thick, I can stick them anywhere, in theory at least. Just imagine that all of this could be printed on foil too, time will tell, and that this could possibly even be done in a curved space. Such possibilities are absolutely fascinating. Anyway, this means to us that there will be another light source available that could in fact be used for any purpose whatsoever.